Welcome to the AP Physics 2 presentation of particles of light and matter waves. Now, in your physics education so far, you've mostly learned that light is a wave phenomenon. It can do things only waves can do, to interfere with other waves. And our discussion of matter, like ordinary, everyday objects that we can see and that have mass, we've treated them as particles or systems of particles. But in the early 20th century, evidence became uncovered that indicated that the situation might not be quite so simple. We're going to talk about that, and we're going to lead into the creation of what is now known as quantum mechanics. The first indication that the situation might be more complicated than was thought was the problems with blackbody radiation. This little video shows bats emerging from caves. Now, the bats are dark and it's dark outside, and so you might be wondering, well, how can they take a picture of the bats? Well, it's because the bats emit infrared radiation, same as you or I. Bats are mammals, are warm-blooded. Anything at the room temperature, thereabouts, is going to emit infrared radiation of some kind. In fact, we tend to call it heat radiation because when we detect thermal radiation or infrared radiation, it feels warm to us. But every object in the universe, it turns out, that has a temperature above absolute zero, which is to say even the universe itself, emits radiation of some kind.
Here's another bat video. You can barely see it, but in a few moments here, they're going to highlight it, and then they're even going to show the tracks of the bats. I really like this one, very colorful. Now, it's called blackbody radiation because it is not reflected radiation. Even if something was totally black, that is to say, it absorbed all the light that hit it, it would still emit radiation. So it is known as blackbody radiation, even though most of the things that they looked at when they were examining blackbody radiation were glowing red hot or glowing white hot. Now, as I said, all objects in the universe emit this blackbody radiation. The thing is that not all objects emit the same amount of it or in the same frequencies. The frequencies of this radiation and the amount of radiation that are emitted depend on the temperature of the objects. Here you can see a graph of wavelength versus blackbody radiation emitted per wavelength. Things that are of a 4,000 degrees Kelvin temperature emit at the lower curve there, and things that have a temperature of 6,000 Kelvin emit at the higher curve there. The higher curve is more peaked in the visible range. Something there would be glowing white hot to us. So you might well be wondering, what's the problem? I mean, classical theory of radiation predicts that charged particles will emit radiation when they're accelerated, and matter consists of protons and electrons and other things as well. Those charged particles, when they're accelerated, i.e. when they move around and they get bounced off of something else, they'll accelerate and they should give off radiation. And we should expect that the more that they move back and forth, the more radiation they give off. So we would expect that the higher the temperature, the more radiation these things would tend to emit. Well, that's all well and good, but it doesn't fit the experimental data very well. This was known as the ultraviolet catastrophe because the misfit between the classical theory and the experimental data got larger the smaller the wavelength. That is to say, in the ultraviolet region especially. At the time when this experiment was being done, they didn't know yet about anything beyond the ultraviolet. But in 1900, Max Planck pointed out that you could do a correction to the classical theory and get a workable formula that matches the data almost exactly. Planck just assumed that radiation is not emitted continuously, but it is emitted in discrete chunks, which he called quanta, which is Latin for amounts. If you make that assumption, you get a curve shown here in blue that almost exactly matches the experimental data that were available at the time. Planck came up with an equation that related the amount of energy carried by one of these quanta of light with the frequency of the light. The equation involved a constant which is now known as Planck's constant in his honor, and it says that the energy of one of these packets of light, one of these quanta, is equal to Planck's constant times the frequency, or E is equal to h times f. Now, in atoms, energy is often measured in electron volts, and so we will give Planck's constant in terms of electron volts. H is equal to 4.14 times 10 to the minus 15 electron volt seconds. You can see that when you multiply that constant times the frequency, which is in inverse seconds, the seconds cancel out and you're left with an energy. What Max Planck called the quantum of light, we call a photon. Planck wasn't suggesting that light acted like a particle, just that it got emitted from blackbody radiation in that manner. But we now consider light to have a particle nature, and so we give it a particle name, the photon. Sometimes when I draw a photon in a diagram, I'll draw a little circle representing a particle, but I will also point out that the wave-like nature of light is still represented in Planck's formula by including a little wave diagram within my particle photon. In SI units, Planck's constant would be 6.63 times 10 to the minus 34 joule seconds. So let's see if we can use this constant to figure something out. Let's say we have a certain radio station broadcasting a radio wave of 100 megahertz, and it puts out 30,000 watts of power. That is to say, 30,000 joules per second are leaving this radio station. Convert that joules per second and that 100 megahertz into how many photons the station emits per second. Go ahead and pause the video while you work on this, and then once you get your answer, start the video up again to see if your answer is correct. The answer that I got is 4.5 times 10 to the 29 photons per second. Here's another question in a similar vein. You have two monochromatic light beams, one red and one green. Now they have the same intensity. That means they have the same total energy per given area, and they cover the same area. How does the energy of each photon and the number of photons in each beam compare? Go ahead and stop the video now, and then start it up again once you have your answer. Since red light has a smaller frequency than green light, red photons will have less energy per photon than green photons. Therefore, you're going to need more red photons per second in order to have the same intensity.